Alright, I think we'll get things started. Hi everyone, welcome to the latest seminar in the Smart Mobility Connection seminar series. My name is Sarah Cho, and I'm a Traffic 21 Women in Intelligent Transportation Fellow. So thank you all for coming here. This is really intended to bring the transportation community together, to hear from our researchers, and create a space where we can collaborate and discuss the recent transportation, what's going on, what researches are happening. And this is actually our last SMC for the semester, but we'll be starting things back up in January for the spring semester. So today we'll hear from Dr. Fang. She's an assistant professor at the Institute of Software Research at the School of Computer Science here at CMU. Prior to joining, she was a postdoctoral fellow at the Center for Research in Computation and Society at Harvard University. She received her PhD from the Department of Computer Science at University of Southern California, her bachelor's in electronic engineering at the Sing Hall University. Her research lies in the field of artificial intelligence and multi-agent systems, focusing on integrating game theory and mechanism design with machine learning. Her work has been motivated by and applied to societal security, sustainability, and mobility. They're really contributing to the theme of AI for social good. She has numerous awards, and we're really excited to have you. So without further ado, please join me in welcoming Dr. Fang.
Thank you for the nice introduction. And today I would like to talk about our recent work, ongoing work, on incentivizing participation in peer-to-peer ridesharing platform. And as I mentioned, this is ongoing work. It's not published result yet. We're still working on it and refine it. And any feedback from you would be super valuable. And this is joint work with Kun Oh, my PhD student, and Yan Han Pan, student from Pepper, and also Professor Alex Josselet. And I also would like to thank Wei Long Wang and Chen Kai Lin, who provided a lot of help to the project. So we all know heard about smart city, and indeed, a lot of the aspects of our daily life have already revolutionized due to the latest technology development, and mobility is one of them. And indeed, we can see that there are driverless cars, there are dogless bikes, and for shared bikes, there are Uber and Lyft and all kinds of ride-sharing platforms that completely changed our way of transportation. However, most of these benefits of the revolution comes to the people who are living in the city, in urban areas. What happens to suburban and rural areas? There are still a lot of challenges there. First of all, there's a lack of public transportation, and for the areas that a population of a disadvantaged population is living, then they would have they lack access to their essential needs if they don't have private vehicles. So there's a big problem there. And of course, one immediate thought is, why not Uber and Lyft operate there? Yes, they are operating, but it's not super useful. If you have ever tried to call Uber from a suburban or rural area, that is not like very kind of wealthy community, then you notice that there's a long waiting time and there's a high cancellation rate because drivers feel like it doesn't worth it to drive all the way to pick you up from that area. And if you do it for daily commute, it will be very expensive. So therefore, alternative is to try to use community-based peer-to-peer ride sharing. That is like not commercial platform like Uber or Lyft, and it can help people to identify carpooling opportunities to share the cost. And also it can help building the community to make it a united community. However, well, of course, there are some existing platforms trying to do this, but they're not so super satisfactory. A lot of them have a very high overhead to use, and it's not super flexible. And also some of them do not provide up-to-date information, or there's no immediate response, even if you made a request. And sometimes there's no community-specific service and do not leverage latest advances in technology, and privacy and security concerns always exist. Let me show just two examples. One is this one, share a ride. what you're asked to do is to submit an application, and it tells you that they will get back to you in 2 business days. And that's kind of like comparing to Uber or Lyft, that's clearly not as flexible and convenient to use. And another platform called Carpool World seems like have more carpooling requests and offers. However, anyone can access it without any sign-up process, and you can see that I just plugged in CMU, and you can see that you can actually find the map. There is a map button, so I clicked it, and surprisingly, it directly leads to the exact origin and destination shown on Google Maps. So clearly, this privacy and security becomes a big concern. And what we are trying to do is we want to support a community-based peer-to-peer ride-sharing platform that can bring smart city technology to the suburban and rural area, and to make it as easy to use as commercial platforms, and provide features specific to peer-to-peer ride-sharing, and also provide efficient matching. So we want to provide something that can look like this on the right, that is like easy to use and kind of straightforward. So of course, to do this, that has 2 parts that we need to do. One is the design of the website or the smartphone application. The other is to design the algorithm that support the running of this platform. In Uber and Lyft, you probably know that they have very complicated algorithm for dispatching drivers to riders, and also complicated pricing mechanism. And for this one, what we are trying to do is clearly, first of all, we want to design algorithms that can efficiently match riders and drivers given their constraints and preferences. And we don't want to end there, because because we also want to ensure fairness and stability of matching. In addition, we want to design rewarding schemes that can incentivize participation. And today we are going to talk about the models and algorithms we developed to support such a peer-to-peer ride-sharing platform. I'll start with introducing the model and notations, and then I'll introduce our algorithm for matching the drivers and riders to maximize system efficiency. And then I'll talk about what is the trade-off between efficiency, fairness, and stability. And I'll briefly mention our plan for designing reward and payment scheme to incentivize participation. And last, we will talk about the plan. And if we still have time, I would like to introduce an additional thread of my work, that is designing the pricing and scheduling scheme for commercial ride-sharing platforms. That has been and we can see like how things are different in commercial and non-commercial systems. Okay, so let me start with the model. So we consider a set of locations denoted by B that is a set of possible origin and destination locations, and we consider a discrete time horizon starting from time 1 to time t. And denote by this to be the travel time from U to V, basically the time if you follow the shortest or fastest path from U to V. We assume that in the system there is a set of riders. For each of the riders they would self-report their origin, destination, and the time window that they would like to depart and arrive. So basically this tau RE is the earliest departure time, and tau RL is the latest arrival time. And in addition, they would report preferred departure time and the maximum detour time that they are willing to allow. And in addition to this basic preferences and constraints, we also allow them to self-report, or the system would try to estimate the value of the trip to them, and also the cost for them to complete the trip if they are not matched to any driver, meaning if they have to take an alternative way of transportation, then how much it would cost to them. And in addition, we assume that the system knows this cost function as an input, which is the cost if the rider is matched to the driver and the rider is picked up at time t and dropped off at time t prime. And this cost, the CTT prime r, is it consists of actually three parts: the travel cost, the detour cost, and the deviation cost. Travel cost is like the base cost, and the detour cost is if the driver detour from its shortest path for the specific rider, how much additional cost it would incur. Deviation cost is if the departure time and arrival time deviates from the most preferred time, how much cost it incur. And we assume this cost is linearly increasing with respect to detour time and deviation time. And similarly, for the drivers, we assume that for each driver, they will self-report their origin, destination, and time window. Notice that this is one key difference comparing to Uber and Lyft, because peer-to-peer ride-sharing, we're talking about people who are in the same community or similar communities who are offering help to each other, and therefore they're not full-time drivers or part-time drivers. They're just trying to go to their own destination, but along the way they may try to provide help to others. So it's important that they themselves have origin, destination, time window, and preferred time, and also maximum detour that they are willing to suffer. And in addition, they will support. There is a value of the trip, and the CT prime D, which again captures the cost if they depart at T and arrives at T prime. And it is again kind of a combination of travel cost, detour cost, and deviation cost. Any questions with the model and notations here? Okay, so next we will introduce how we are going to match the drivers and riders to maximize system functions. Well, the simplest way to do optimization, the simplest optimization goal in this case is to minimize the total cost. It's kind of straightforward. Everyone has some cost of traveling, then we want to minimize the total cost. And if we use CDS to denote the minimum total cost of driver D and a set of riders S, when D is matched to pick up riders in S and pick up and drop off riders in S. Then given the matching pi, we can let us denote the set of riders picked up by the driver as S pi D. Then this objective function would be minimizing the total cost for all the DSs that are matched together, plus the additional cost for the riders who are not matched. By the way, here S can be empty, so it's like for each driver, it can be matched to an empty set. However, for the riders, if he's not matched to anyone, he has to pay this lambda R, which is a cost he needs to pay, say, to take public transportation or Uber or other type of transportation opportunities to get there. And then our goal is to find the best matching pi to minimize this total cost while satisfying all the constraints of all the participants. Okay, so how can we find this best matching? We propose a two-stage algorithm where in the first stage, try to compute the CDS for all the feasible DS pairs. So D is a driver, S is the subset of riders. And if D is matched to a subset of riders S, then D is responsible to pick them up and drop them off, and then go to his own destination. So therefore, we need to find all the feasible pairs, and also for each feasible pair, we need to compute the optimal schedule that can lead to the minimum cost for the riders and drivers. So what is the schedule here? Schedule means of course, this driver leaves his own origin, and the schedule means when does he leave his own origin, and what is his stops along the way, and when does he need to arrive at each of these waypoints or stops along the way, and finally he will get to his own destination. And in the second stage, meaning after we get all these DS pairs and the CDS for each of them, we are going to try to find the best matching, and to minimize the total cost for all the drivers and riders. Okay, so let's look at stage one. What we are going to do here, we follow the Rtb Graph Approach, the framework proposed by Alonso Mora et al. In 2017. Essentially, it's a rider trip vehicle graph, and the key idea here is that a DS pair is feasible only if the DS prime pairs are feasible for any S prime that is a subset of S. So it's like if it is feasible for a driver to pick up me and Lisa K, for example, then at least it has to be feasible for the driver to pick me up separately and pick Lisa K up separately. Only if these conditions are true, we can consider if whether or not the driver can pick up us simultaneously. So that's the key idea. And the algorithm is very simple. If we keep a superset Si or like a abstract set Si, that is the set of all the subsets of riders that can be compatible with the driver D and has size I. And we will initialize all these sets as empty sets, and we will start by increasing the size of the subset from 1 to R. R is the number of riders, and we will enumerate all the possible feasible subsets of size I given all the feasible sets of size I minus 1. And then for each of the feasible subset S, we will check the feasibility and compute the CDS and optimal schedule. If it is indeed feasible, we will add it to the set, the abstract set Si. So now the only challenge here is how can we check the feasibility and compute the CDS and find the optimal schedule. And here we propose a novel algorithm that can find the best sequence of waypoints through tree search and enhanced by pruning, dynamic programming, and imitation. So what does that mean? I'm not going to go through the very details, but I would like to give the high-level idea. So we want to search a sequence of pickup and drop-off waypoints, and then we will prune, and that can be viewed as a search tree. And then we will prune the search tree if we can identify a lower bound of cost in that subtree. And if that lower bound is higher than the best solution we get so far, then we will just ignore that subtree. And at each leaf node, meaning once we identified the whole sequence of picking up and dropping off, we only need to determine when exactly the driver needs to reach that waypoint. And we show that this part can be solved by dynamic programming. And in addition, we notice that if we can get a good solution before the tree search, we can significantly prune the tree. So it is important to use some kind of heuristic approach to get a reasonably good solution before the tree search. And what we notice here is that we can imitate what we have done for a subset of riders. So if I try to determine what is the best way for the driver D to pick up, let's say A and B and C, then we can at least learn from how this driver would pick up A and B only. Would he pick up A first, or would he pick up B first? And we try to leverage that information to determine a good schedule for picking up A and B and C. Okay, so as an example, if we do have this riders 1, 2, 3, then of course we know that the driver would start from his origin. Here it has to be type. So the first waypoint for the driver to visit is his own origin. Right? There's nothing else he can do. And then after that, he needs to determine where he should go next. Would he try to pick up rider 1, meaning go to the origin of rider 1, or pick up rider 2, or pick up rider 3? Well, there are all possibilities. Let's just leave it in the search tree, and then we can continue. If we take the first pass, and if the driver indeed pick up the rider 1, then what is the next waypoint he should visit? Well, he can drop off rider 1, or he can try to pick up rider 2 or pick up rider 3. And then we can look at, for each of the subtrees, what is the minimum cost that the driver has to pay. So for example, if we are at this point of dropping off rider 1 here, it's hard to see, then the minimum cost that can incur is clearly for the driver to then pick up rider 2 and drop off rider 2 and then go back to his own destination. So this is like a lower bound of the cost he has to incur. And of course, we can design more complicated calculation of the lower bounds, and we do have an algorithm to do that. And what we found is that using these lower bounds together with this imitated together with the heuristic route we found by imitating the pickup sequence for a smaller subset, we can indeed prune the tree significantly and find the solution relatively efficiently comparing to without doing any pruning. So that's for stage 1. And for stage 2, we try to find the best matching. And in this case, we can solve it through integer linear programming. And this is again similar to the Alonso-Mora part. And as we can see, we use xds, which is a binary variable indicating whether driver D is matched to subset S. And yr is again is another binary variable indicating whether rider R is picked up or not. Okay, so the first constraint says for each rider R, he's either matched to one of the drivers or not picked up. So they have to sum up to 1. And the second constraint says for each driver, he can only be matched to one of the subsets. And the third constraint says if DS is not a feasible pair, then XDS is 0. So it's kind of quite straightforward, and it works well. But the question is, what is the limitation here? Is this cost minimization enough? One thing we noticed is that this formulation does not explicitly reason about the rationality of the drivers. Basically, like, why do the drivers even participate in such a system, although he may not get any payment from the riders? Well, yes, of course, he wants to reduce the total cost of the society. And maybe he also feels good by helping others. These are like the two obvious incentives for the driver to participate. But when would the driver be unhappy? Well, if the driver suffers too much additional cost due to the tool and deviation, but his contribution to the whole system, like the saving in the cost or the help he provided to others, is not so significant, or is not as significant as he wanted, then he may feel unhappy. So we want to take into account this kind of happiness or utility for the driver explicitly into the model, and therefore we propose this utility model for the riders and drivers. For the riders, we assume that it's straightforward. The utility is simply the value of the trip minus the cost he needs to pay. If he's matched, then his cost is CTT prime R, meaning his cost when he's picked up at time t and dropped off at t prime. If he's not matched, then he has to pay this lambda R for the alternative transportation, alternative way of transportation. And for the driver, similarly, his base utility can be viewed as the value of the trip, VD, minus his cost, total cost of depart at time t and arrives at t prime. However, as we mentioned, he may want to help others, and he feels good by helping others. So in literature, studying altruism, some of the literature uses this notion of altruistic factor, Rtb, and basically the perceived utility for this driver, or the altruistic utility for the driver, is his own utility, plus Rd multiplied by the utility of the riders he helped. So that's a straightforward and intuitive explanation of the utility of the driver when he feels he gets benefit by helping others, feeling good by helping others. And then in this optimization problem, we need to add this constraint that for every single participant, it is individually rational for them to participate by constraining the utility for each of them to be non-negative. And for the driver, here we use the perceived utility because the base utility can be interpreted as Rd equals 0. So now we have this refined optimization problem. We have the same objective function of minimizing the total cost, but subject to the constraint that every single participant has non-negative utility. And of course, we have to satisfy all other constraints. And the original optimization problem is essentially equivalent to the case where Rd equals infinity. Okay, so how can we design or modify the algorithm to deal with this refined optimization? Actually, the algorithm are almost the same, and they are all applicable except for one point. where we try to compute the CDS for a specific ES pair, meaning for the specific driver and subset of rider pair, we want to find out the minimum, like the best schedule for them, while considering this additional utility individual rationality constraint. And what we found is that we can solve a integer linear program if the solution of the dynamic programming is not individual rational. And we designed this integer linear program for it, and I'm not going to go through each line of it. I just want to mention that these two lines are representing the constraint that the utility for the rider is non-negative, and the utility for the driver, the perceived utility or the altruistic utility for the driver is non-negative. Okay, so here are some simulation results. We tested the scalability of the approach. We simulated instances trying to reflecting the daily commute in the neighborhood. Basically, we're saying that all the riders and drivers would start from this block in the middle, and their destination is randomly sampled from these big blocks. Most of their destinations are sampled from these big blocks, and for the rest of them, it's just randomly sampled for the rest of for any part in this grid in this grid. And it's kind of reflecting the fact that for the community members, they probably are hired by a few big companies, and for the rest of them, their destination is more random. And we set the capacity of each driver to be 4. Oh yeah, I probably missed this point. So each driver has kind of a capacity, how many seats he can provide in his vehicle, and we set this number to be 4 here. And we can see that when we change the driver to rider ratio on the x-axis, the runtime changes significantly, and in fact, the runtime is highest when the ratio is 20%, meaning for each driver, there are 4 times the riders or rider requests, and it means that kind of like it's equivalent to when the cars can potentially be fully utilized. And in this case, the runtime is the highest. And then we fix the driver-rider ratio to be 25%, and then we try to increase the number of total participants. And as we can see, the algorithm can run up to 160 participants within an hour, and we're still working on how to further improve it. And the simple improvement can be done by parallelizing the computation, because in our whole framework, the DS pairs for different drivers Ds can be computed in parallel separately. So if we have enough CPUs that can run in parallel, we can significantly improve the scalability. And in addition, we also considered other simulated environments that reflecting non-rush hour commute in the neighborhood, where again all the origins are from the same block and all the destinations are completely randomly chosen. And in this case, what we found is that our algorithm can handle problems with much larger scale. The intuition is that because the destination becomes more random, the feasible sets between driver and subset of riders become less. So it's easier for us to scale up. Yes, question?
You say that you pick the location randomly.
Yeah.
Do you still characterize whether the random location it could be more difficult to get to than others?
Yes. So because it's a grid and because there's no blocked destination, so if the flexibility time window is fixed, then it becomes much harder to pick up 2 riders simultaneously, for example. Yes.
So in your experiments, is that a one-shot thing that you do a centralized assignment for the coming hour, say? Or is it something that has to run in real time, so you need to get feedback in a second, or because you have a running time up to 1 hour, but that means there are only a few people in the system. So how does that work out?
Yeah, so here we are assuming that we can get the request ahead of time, so it's not running on real time. If it is running on real time, then we need probably some more heuristics and to adjust the algorithm to fit the real time requirement. Yes.
So you talked about how optimizing picking up the riders for the driver. Did you think about, or does the model consider finding the optimal route? So like I'm picking rider 1, and then the rider 2 shows up on the system. program show up which is closer to rider 1, it's after rider 1,
Uh-huh.
or is it before rider 1, and then change, reroute the driver's patient to rider 2 before rider 1, because that's much more economically
Yeah.
efficient.
Yeah, great point. So you're asking about the dynamic rerouting. And for now, we are not considering that yet. We are still considering the case where we have all the requests ahead of time. And for the future work, we definitely want to adapt that case. Yeah. And we mentioned this altruistic utility. And we all know that in many systems, we talk about maximizing social welfare, where social welfare is the sum of the utilities of all the participants. Then let's take a look at how this cost minimization connected to the utility maximization. What we notice is that, first of all, minimizing the total cost is equivalent to maximizing the total utility, which is not perceived utility, it's just the base utility for the drivers. Then we say that, of course, given that the alternative optimization goal is to maximize the total altruistic utility, meaning the altruistic social welfare, where instead of summarizing the utility, the base utility of the drivers, we're summarizing the perceived utility of the altruistic utility of the drivers. And this is, again, can be, here is maximization, sorry. And again, it can be converted into a minimization problem of the measured by the cost, but it's more complicated than what we did before. One thing to notice here is that if this, what's the difference between these two? If rho d is high, if this altruistic factor is high, then it is possible for the second system, which try to maximize the altruistic social welfare, to force the riders to be picked up by a driver, even if even if from the system level of minimizing the total traveling cost is not so efficient, because by asking this rider to be paired or matched to the driver, this driver has a lot of altruistic utility. He feels really happy, and then by summing up the total utilities, we feel like, oh, it's good to match this rider to the drivers just to make the driver happy. So it's kind of the trade-off here, but we did run some experiments to see how much difference it can lead to. And we tested 5 drivers and 20 riders when we noticed that the solution is almost the same when the rho d, the altruistic factor, is low. However, if rho d is high, then the difference in the total utility or the total social welfare can be as high as 16%. And here on the x-axis, we show the altruistic factor, and on the y-axis, we show the total utility, and this ASW means the altruistic social welfare, and this X star ASW is the optimal solution when we try to solve the problem of optimizing the altruistic social welfare. So, and the blue line here is the altruistic social welfare when we use the solution that is optimized against just a simple social welfare. So as we can see here, there is a gap between the blue line and the red line, but when the rho is small, less than 1, then they are exactly the same, which is expected. And similarly, we can compare the social welfare for the 2 optimal solutions, and we can see again they are almost the same when the rho is small. Questions so far? Okay, so next I would like to introduce the trade-off between efficiency, fairness, and stability. What is fairness? Well, what is the problem? Let's first ask, what is the problem with the current matching algorithm? A rider who is slightly dominated by another rider would never get a ride. Consider the case where driver A can be matched to either rider B or rider C, who are living very close to each other, but B is right on the way and C is slightly off the way, and they are all going to CMU. Then, if we use the cost minimization algorithm, we are going to ask driver A to pick up B and then go to CMU. And C will never be matched. No matter how many times he entered the system and requests a ride, as long as B is there and A is the only driver, he will not get matched. That's clearly not so fair per se, because especially when this is a frequent and repeated request, rider C deserves some kind of match, because it does not lead to too much detour, and if he never gets matched. He has to pay a high cost of lambda r himself, and it's like not so fair from an intuitive perspective. Therefore, we define fairness. Therefore, we design this new optimization problem where we try to ensure that each participant I is matched with a minimum probability theta I, as long as there is a feasible match for him. And for now, let's assume that theta I are all the same for all the riders. Okay, so, and how can we find such a matching? Then we need to allow for randomized matching. So we're trying to find out a probability distribution over all the possible matchings, such that for every single rider, his probability of getting matched is larger or equal than theta I. And let's denote the feasible matchings to be M1 all the way to M beta. And this each feasible matching is indeed a matching. It's like a lot of DS pairs where each driver D is matched to some set of riders. That's called a matching. And we use MIL to denote whether or not a participant I is matched in this particular matching. And we can write down this optimization problem where we try to minimize the total cost, cost ML multiplied by the probability that we choose matching L, subject to the constraint that it has to be a probability distribution, so the probability is sum up to 1. That's the first constraint. And the second constraint says the probability of each participant being matched is larger or equal than theta I. And of course, the probability has to be non-negative. But the challenge is, it's very hard to solve this problem as is because there's an exponential number of feasible matchings. And we propose to solve this problem by using constraint generation for the dual problem. We derive the dual, and we show that what we can do is we don't consider all the matchings altogether. We start with a few number of matchings to see how we should randomize over these matchings to get an efficient solution. And then we try to look at how we can find an additional matching that can significantly improve the overall objective, meaning minimize the total cost in this case. And that can be viewed as by solving a slave problem, and we observe that slave problem can be converted as another matching problem, just with the edge weight, just with the CDS changed from CDS to the C bar DS, which is a small change from the original solution using the optimal solution of the dual. So with this, we can quickly solve this optimization problem, and in the simulation results, we find that the minimum cost it increases linearly as theta increases when theta is small. And that, what does that mean? It means that we can increase fairness without too much degradation in the efficiency. And we're still working on further analysis on this, and especially when theta becomes higher. And another thing that I want to mention is the stability. So what is the stability? Notice that this is not like Uber and Lyft. It's a community-based matching. And we need to ensure that the matching is stable in the sense that no one or no subgroup of participants want to leave the system and operate on their own, kind of form their own ride-sharing schedule because they dislike the current schedule. And why would they dislike the current schedule? Because their utility is lower comparing to if they operate on their own. So we want to add additional constraint to ensure this stability. And simple case is when this subgroup has size 1. Then we will have the constraint that for each rider, his utility of participating in the system has to be larger or equal than his utility of just taking his alternative way of transportation with the utility of VR minus lambda r. And similarly for the drivers, this constraint says if the driver operates on his own, do not take any riders, and departs at his preferred time, then his utility is on the right-hand side, BD minus CTT prime D, where this T and T prime is just his preferred time, departure arrival time. And his utility when participating in the system has to be larger or equal than this value. Of course, this is only for the subgroup of size 1, and we have to reason about subgroups of all the sizes. And that would lead to a lot more additional constraints on the system, on the optimization problem. And we're still working on that. And the intuition is that adding the stability constraint would reduce the system efficiency or the total cost or the social welfare. And based on this, we would try to see, okay, can we help improve the efficiency by some kind of reward or payment scheme? That's the work that we want to do in the future. What can we do here? We have already built this basic framework such that we can list out the few options we have. The first approach is we can build a scoring system such that the theta I, the guaranteed probability of getting matched, can be calculated based on the scores of each participant. For example, if a driver ever provided a ride to others, and then next time when he becomes a rider, he may get an additional score that can increase the probability, the base probability of being matched, the theta I. And similarly, if the riders frequently participate in the system, we can also increase the score of this rider to incentivize more participation. And the second approach is to provide external reward to ensure stability. We're saying that adding the stability constraint would reduce the efficiency, but what if we tell the person that, yeah, we know that if you operate on your own, you can get higher utility, but if you stay in the system, we will give you some additional reward. For example, it can be a coupon from the community stores or some other community partners, or there can be a raffle at the end of each season, such that the participant has more incentive to stay in the system instead of operating on their own. And the third approach is to suggest a payment from rider to driver, because for as we talk to our collaborators, we noticed that most of the community members are okay with payment, at least share some of the gas cost. Therefore, we also want to analyze how can we potentially design the payment scheme such that all the participants are happy and can further increase the participation. So eventually, we want our algorithm to be deployed in the real world, and we're in collaboration with Lawrence County and Allegheny County Department of Human Service Office of Community Services, and also a community called Houghton Albers. And Professor Alex Jacquillian has already developed this basic framework of website that supporting the peer-to-peer ride sharing for Lawrence County. Here's just a landing page of the website, and each participant can choose whether he wants to request a ride or provide a carpool, and he needs to fill a form for if he's requesting a ride or providing a carpool opportunity. And we are hoping that our algorithm can be embedded into the back end of this website so that we can do the matching for them efficiently. So to summarize, we talked about peer-to-peer ride-sharing platform, and the highlight is that we would like to consider the utility model of the participants in addition to total cost minimization. And we also analyze the trade-off between efficiency, fairness, and stability. And in future work, we want to design reward or payment scheme to further incentive participation. So that's all for the talk. And we do have, if you're interested, we do have backup slides on how to deal with the pricing and scheduling in commercial ride-sharing platforms. So with that, I'm happy to take questions. Yes.
I was just wondering how the current, you mentioned there are some existing systems, kind of right now, how do those work, and how much time in advance do you have to basically specify that you want a ride?
Yeah, so as we shown in the two examples, in the first one, you have to wait for 2 days for them to get back to you, and basically they are kind of like emphasizing on this repeated weekly or daily commute options. And the other platform is like you can go to the platform and look for the opportunities on your own. It's more like a Craigslist kind of thing. And And I think for the first one, where you have to wait for 2 days, it's probably more like a manual matching process. And for the second one, there's no need for matching algorithm because every participant is responsible for finding the partner on their own. Yeah. And we are trying to provide such algorithmic support for a more systematic platform. Yes.
Can you comment on how many riders don't get matched? I mean, that seems to me to be a very likely possibility since you're not constraining destinations or origins at all.
That's true. Yeah, we don't have the report here, and that's a great suggestion. We will try to analyze that, especially for different scenarios. Yeah.
I think you'd get a higher match if you were, say, going from Orange County to Pittsburgh or something.
Yeah. Yes.
Talk about some riders can be dominated by other riders.
Yeah.
So I heard some application that they ask the riders to go to walk to the major street or some major road. So does that fix this domination?
Yeah, that's a great point. Indeed, we can potentially add that take that into account. Of course, walking to that location would lead to additional costs for the rider, but it's potentially better in terms of the system level's cost or CO2 emission, for example. Yeah.
How are you ensuring the number of riders and drivers remains fairly same?
Oh no, we do not ensure that. We are just in the simulations we tested when the ratio changes from 10% to like 20% something, 10% to 100%. Yeah, we actually did that ratio. We actually adjust the ratio between the drivers and riders.
But if you were to deploy it, it is a potential problem that you will have to consider.
What kind of problem that you're suggesting?
If more number of people are willing to become riders than the drivers, then
that's true. So it's possible that when we deploy it, the ratio can be less than or larger than this KD. KD is like the number of available seats in each vehicle, and there's, I think one alternative is that, for example, the community itself can provide some additional help, like providing an additional vehicle just to supporting this ride sharing, but that will be out of scope as for now. Right now, we're still considering all the riders and drivers coming from the community themselves. Other questions? Yes.
Is it possible for people who, when they're posting a carpool, I guess I'm wondering, is there any way in the system to accommodate people with children? So if somebody needs to carpool somewhere with, like, they're going to an office with a daycare center or something like that, and they're taking their child along, would some drivers be able to say, like, I have a car seat in my car?
Yeah, that's a great point. Yeah, so we want to incorporate those special needs when we actually get to the deployment phase. That will be additional features that we can add. And from the algorithmic perspective, that does not lead to too much difficulty because that's just a simple feasibility constraint. Yes?
Doesn't Waze do this right now?
Ways do this? I'm not aware of it.
Just like saying everyday commuters going back, so you have extra seats, and it's just based on cost of gas.
So what we are doing is different from that. So we're not, the system is not paying them for the gas. It's more like we're trying to pair the community members together, trying to help them to find ride sharing opportunities that can be beneficial.
Do you think that some sort of consistent financial incentive would be a better way to ensure value in this?
So that's exactly why we are trying to talk about reward and payment schemes that can further incentive participation. And what I think would be sustainable is not the system paying everything for them, but instead either they pay, there is some external incentive provided by the community partners, or the riders pays to the drivers with some suggested amount.
This may be a question for you. Wouldn't that be some sort of a salary advocating?
Yeah.
As opposed to a reward?
Yeah.
Based on
How should I? I'm greedy. I'm sorry. I like to know when I'm going to be paid for something. I feel like a lot of people are the same way too.
Yeah, so we do consider like how should we design the payment scheme such that it becomes more kind of sustainable per se, without considering too much altruistic incentives. Yes.
Maybe this will be the last question, but so it seems like the difference with Waze and what you're proposing is the massive users, right? The massive users. Have you made any calculations to the number of participants that you need to have a successful deployment?
Yeah, that's a good point. So, I guess what you're trying to say is that how much saving we can see if there's only like one participant versus 100 participants. And it's not surprising to see that when there's a large number of participants, the system provides better solution or higher benefit. And we haven't done any analysis on exactly how much we can save as the change number of, or the percentage of benefit as we change the number of participants. And that's very interesting. Other thoughts or questions? And by the way, if you're interested in the pricing part, we did some analysis on the pricing case, especially for Uber, or Lyft, this kind of commercial ride sharing. And what we found is that we need to do spatial temporal pricing, such that the drivers has incentive to follow what the system asks them to do. The spatial temporal pricing means that when you determine the price, you're not only determining the price according to the current demand-supply ratio, but also the future demand-supply ratio. And in fact, we designed a algorithm that make use of the mean cost flow and its dual to determine the competitive equilibrium, to determine the right price for the riders to pay the drivers. But that's for the system where it's a commercial system and each driver can only pick up one rider.
I'm sorry. Waze is really simple. It plugs in how much gas you use based on where you plan to look and where you drive, and that's how you get paid. That makes a lot more sense. Your advanced stuff, I just can't understand.
Yeah, we can discuss offline to see what we can leverage from what Waze is doing.
Just a question for you. How does Waze deal with the carpooling?
You go on the app, say, hey, I'm ready to carpool, then it'll say there's someone on your route, then you pick them up, drop them off on your route.
How far away from your route?
Normally less than a mile. I mean, you're getting paid, and you're trying to solve this problem. So, for an altruistic individual use that. I mean, I don't use it. If I wanted to drive people to work, I'd use Uber or something like that for them.
Thank you so much, Fang.
You're done. You're done.